In this video, we will consider the relationship between Gibbs free energy, the equilibrium constant, and the cell potential for a galvanic or voltaic cell. In this galvanic cell, we have a copper and zinc cathode and anode respectively, and our zinc anode is oxidizing to produce zinc ions in solution and electrons that go outside the cell to perform work. These electrons then recombine at the copper cathode with copper ions from solution to make copper solid. And then anions flow across our porous disk, which is acting as a salt bridge to balance the overall charge in solution. In this problem, we will calculate the Gibbs free energy of reaction and the equilibrium constant for the copper-zinc galvanic cell at 25 degrees C. Since we don't know either, we're going to have to find something else that can help us relate delta G and K. The hint for solving this problem is that if we find the Ecell, or the standard cell potential, from this copper-zinc galvanic cell, then from that value we can determine both delta G and K. So our first step in solving this problem to find delta G and K will be to determine the Ecell. The next step would then be to directly calculate delta G from this Ecell, and the final step would be to also calculate the equilibrium constant. In our first step to determine Ecell, we need to find the standard reduction potentials for both copper and zinc from a table. We find that for copper 2+ being reduced to copper solid, our standard potential is 0.34 volts, and for the same process for zinc, our standard potential is negative 0.76 volts. So one method of combining these standard reduction potentials to find the overall cell potential would be to take the half reaction that's more negative and consider that to be the oxidation reaction. And so then we take the standard potential for the reduction reaction of copper, and then we subtract the standard reduction for potential for the reduction reaction of zinc. And when we do that, we find that the overall cell potential is 1.1 volts. An alternative way to do this, starting with our two standard reduction potentials, is to flip the zinc equation and write it as an oxidation half reaction. One advantage to this is then we can easily add the two reactions together and look at the overall reaction and ensure that our electrons cancel. If we flip the reaction the way it's written, then we also need to flip the sign on the standard potential. And then we would add the reduction potential of copper and the oxidation potential of zinc. And we still end up with the same overall Ecell of 1.1 volts. In our second step then, to directly calculate Gibbs free energy of reaction, knowing our standard cell potential, we use this equation, delta G is equal to negative N times F times E, where N is the number of electrons transferred, which was 2, F is Faraday's constant, and the Ecell we determined previously to be 1.10 volts. The units of a volt are joules per coulomb, and so when we apply these units to this equation, we find an overall delta G reaction of negative 212,300 joules per mole, or negative 212 kilojoules per mole. So then our third step is to calculate the equilibrium constant. We now know the Gibbs free energy of reaction from step 2, and we can relate that to the equilibrium constant with this equation where delta G is equal to negative RT times the natural log of K. We need to rearrange this equation to solve for K, and when we do so, we have it written here, E raised to the negative delta G divided by RT. We plug in the numbers here. Notice that we're using the R value, that's 8.314 joules per mole Kelvin. When we're using this R value, we have to make sure that our Gibbs free energy is in units of joules per mole, not kilojoules per mole. And we also have to make sure that our temperature, 25 degrees C, is in units of Kelvin, 298 K. So then we find that our KEQ is equal to 1.64 times 10 to the 37, which is a very product-favored reaction, and that correlates well with our very negative delta G, and also correlates well with our high Ecell value.